All right, we'll go ahead and get started. This is the MCube seminar, and I'm very pleased to welcome Will Chapman. He's a project scientist in CGD at NCAR and works on the multi-scale machine learning and coupled Earth system modeling, or M2 LINES project. He earned his PhD in oceanography from Scripps, applying deep learning to embrace US West Coast weather, and went on to join NCAR as an ASP postdoctoral fellow in 2022. His current research focuses on hybrid machine learning dynamics modeling and full climate model emulation to improve predictions of extreme weather events. Welcome.
Cool. Is that mic on? Yeah? Y'all can hear me? Great. Well, first off, thanks so much for inviting me here. I'm really stoked. I have been a MCube visitor here for a bit. I have an office over here, just out of the kindness of MCube's heart, so I really appreciate that. So I am up the hill at the Climate and Global Dynamics Lab. I want to acknowledge that while this science was done at NSF NCAR, it was really funded by the M2 LINES project, which is a Schmidt Sciences funded project, and it's been a real pleasure to work with those folks. This is a big collaborative work, so a lot of people have touched this science, and I will mention them as we go through the presentation, but I want to say a big thank you to the rest of the M2 LINES team, to the NSF NCAR software engineers who have just been like unbelievable throughout this process, and also to the Institute for Computing for Climate Science at Cambridge, ICCS, who have developed a lot of software that I'm also using here and have been amazing partners. So the introduction to this talk will be a little bit preaching to the choir to this crowd, but like choirs like preaching to, I think. So we'll run with that. Where's the clicker? Cool. So let's frame this up with some big science challenges and big open questions within our field. So our ability to predict the weather and climate has improved dramatically over the past few decades, and here's a figure by Bauer et al. Showing model skill on the x-axis, or years of development on the x-axis and model scale on the y, and you can see that we're slowly getting better at predicting the weather. There's this big gap in the southern hemisphere and northern hemisphere that's slowly closing in our satellite era. But really this has been a triumph of understanding the physics and encoding those into computer models and being able to predict them forward in time. And that's amazing because we rely on these models to predict extreme weather, long-term trends, associated climate risks of a warming planet. So these models inform on our policy, our infrastructure decisions, and our disaster preparedness, and we should be really, really proud of the fact that we've encoded this knowledge and they're now having such a big impact. Like, pat ourselves on the back. This is like a really, really cool thing that we have done as scientists. However, despite these advances, we still face fundamental barriers to reliable prediction. So extreme events will catch us off guard, models disagree on future climate trends, and we don't know how to quantify yet the limits of predictability. It's still big open questions. So these are three big weather-driven disasters that have affected folks that are close to me. So the LA fires that recently happened driven by the Santa Ana winds. I grew up in the LA area. Atmospheric river event taking out the Highway 101 here, limiting access to one of the most beautiful places on Earth. This is Big Sur, California. And then the big Arctic air outbreak in North Dakota. I have family up there, and they're all texting me, asking me what was going on. And I told them one thing, and then NOAA put out a report later going, like, it definitely wasn't that thing. So I didn't follow up with them. So the fundamental problem with predicting these is the heart of the climate and ocean system itself. So these are chaotic systems, they're multi-scale, they're nonlinear, and we will always face challenges of predictability in the long range. However, at the same time, we know that in our models we have errant and biased physics. And if we can start to correct that physics, potentially we can start to improve our forecasts. So the biases and uncertainties still remain and limit our ability to predict these forecasts. So this combination, chaos plus bias, limits how well we can predict short-term weather and long-term climate response. It creates persistent biases within our model and ultimately leads to uncertainty in decision-making, which is the big piece of what we're trying to do here. So the big idea I want you to take away from here is that the climate system has intrinsic limits, but there are also large gaps in our understanding and the way that we're representing the physics within those models. And if we can improve those gaps, hopefully we can improve our our predictions. So I'm going to talk about two methods in machine learning that we've been doing to try to impact these spaces. And we'll go through a couple studies. So this first one, I'm calling improving climate model bias and variability via convolutional neural network-based state-dependent model error correction. And this is work that I've done closely with my collaborator, Judith Berner, over here. And she's been instrumental in this process. And if you want to read about it, it recently came out in GRL. It is a big effort pushed forward by this M-squared lines project. So M-squared lines is trying to attack the biases within our coupled climate models. So where are those biases coming from? So first off, we know that they're coming in from our parameterization schemes. We have errant physics captured on the subgrid scales that we know we can improve on. Secondly, in order to solve the fundamental equations of the atmosphere, we know that we have to discretize them. There is discretization error. There are some errors that are leaking in just from our numerics. So these are two big sources of errors. And in M-squared lines, we're trying to attack these biases in sort of a multi-pronged approach. So a lot of our team is looking at high-resolution models or observations, hoping that they represent these figures better or these features better, and developing parameterization closures within this space. They then write a machine learning method that can learn those closures. We plug those into our climate models, and hopefully we have an improved climate. The second sort of pathway, and the one that Judith and I have been looking at closely, is producing error corrections derived directly from our observational products via data assimilation increments. So trying to examine the increments, learn some sort of mapping on our model-based corrections and structural errors that then improves our climate model space. So let's dig into that a little deeper. This is where we're going to focus today. So I use data assimilation quite liberally here because in this study we are actually just using nudging. So I apologize to all the DA experts in the room. But let's look at nudging, and we'll say this is an ad hoc version or a cheap version of data assimilation for us. So what is nudging? If we look at evolving a model state here, we're trying to take our model state x of t, force it, evolve it in time. So we're using our climate model here. I'm representing with this small f. Nudging is an extra parameterization term that is a function of the current model state and also our observed state. And all we do is have a linear relaxation from our model state back to the observed state on some time scale and weighting. So a couple parameters here. And this is a diagram explaining exactly what that is. So if we have the model state evolving in black here, and we have some reanalysis product in teal, all we're doing is adding essentially a tracking or a parameterization space that will then ensure that we are evolving the atmosphere such that it looks like the reanalysis state. So what we're going to do is we are going to grab these nudging increments, as I'll call them, or I'll call them nudging tendencies or increments. I'll probably interchange those words a little bit. And we think that these are representations of some of the error within our model. So let's talk about that a little further. So this is a schematic by Rodwell and Palmer back in their 2007 paper. Essentially what this looks like is a healthy model that has a DA system attached to it. So in the OBS state is in the gray line. Then we have a DA forecast system. So at every point we are forecasting, then the data assimilation increment corrects us back to it. And you can see it's sort of random in time. So that's what a healthy model should look like. In an unhealthy model, we'll have a state that looks something like this. So consistently, the model will be drifting in one direction and the DA is always pulling it back. So you can imagine like this being a model slipping into too cool of an SST, and the DA system's going, hey, we got to warm this up consistently. And that is evidence of some systematic model bias within that state. And the ultimate goal would be to say, okay, can we point back to some sort of process within our model, learn something about the errant physics, and say, if we corrected that, we could correct these error states. So if, for example, in, yes, the Rodwell and Palmer paper, they pointed back to their convective processes over the Amazon. They said, okay, it's likely our convection scheme that is leading to the dominant portion of these model increments. So the big idea is for a climate model that the amplification of some forcing on some bias process will occur on the timescale of decades. When we look at biases in our climate models, we run them out for 30 years, take a difference between our observed state, and we say, you know, we got some biases here. However, the intrinsic timescale of those processes are typically associated with the order of hours. So this is time step to time step errors in our parameterizations that could be accumulating and turning into a biased model state. So that is really evidenced here by my colleague's paper, Will Gregory. This is in the GFDL SPEAR system. And what you see on the left is the bias in the sea ice concentration. On the right is the average increment as they move across that space. And you can see they kind of map onto each other one-to-one. Basically giving this idea that if you could correct the biases here, correct on the increments on the fast timescales, it would reflect on the climate state itself. So the big question that we're trying to ask is, can we write some function generator which takes the current model state, x of t, and just maps them onto these nudging tendencies? And in that way, we could get rid of the obs itself, and we were just trying to learn the model. So let's lean into that a little bit more. The nudging is currently a function of x of t and the obs, and we're mapping to some nudging here, this purple arrow. So we have our state and we have some obs. Really, that's a function of two things. One is it's holding a trajectory, chaos management here, as I'm calling this delta, or this tilde n. But additionally, it is a big component is like the model error itself. And we're hoping that we can write the machine learning algorithm such that we just target this component here. So we're going to define a machine learning function here, I'm calling f of b, that maps the model state to the nudging increment. And in that way, we can then run the model online without the observations. Now we have a completely independent model state that is just correcting for the model error itself. So to make this really clear, if I launch this model over and over again, we're not going to see the same model simulation. It's not always going to look like the reanalysis, but we're hoping that we have a representative climate model that explores the full attractor, but has less bias within the state because we've learned to correct it from time step to time step. So we'll represent that here. So I spent a lot of my time post-processing models. I used to post-process forecasts. I did a lot of work in this space. So why not just post-process the model? So let's do a little thought experiment. Let's say our SSTs are too cooled there. This is a really sensitive region, and we know there's a convective threshold in the tropics, so we're not going to get enough convection. That convection will not send upper-level divergence to interact with the jet, which won't spark Rossby waves. Then we don't get rain in Southern California, and we need rain in Southern California, trust me. So there's no post-processing algorithm in the world that can correct this whole dynamic chain. What we're hoping is if we can catch the models at the source, it will lead the model to explore the attractor more. So by correcting the model at runtime, we are hoping to allow the state to access new parts of its own attractor. And this is demonstrated really well in a figure by Judith. Essentially, she's using stochastic parameterizations to kick a model out of a potential well, where it was only exploring unimodally before. And if you can kick it out of its potential well, it can explore more of its probability space here. So that's the big idea we're kind of trying to track. So how are we going to do this? First, we'll run CSM version 2.1.5 for 10 years, and we're going to nudge to the era 5. So I acknowledge right off the bat, the era 5 is not observations, it's a reanalysis product. So we are inheriting all of the errors of era 5. So we nudge to era 5, and we're going to collect those model increments. We then write a loss function that says, okay, we want the output of our neural network to minimize the distance between those increments and the prediction from the model. So we'll split that into train, test, validate, standard practice in machine learning. We will train on this period, tune on the validation, and then have an independent test set. We then rewind the model back to 1979. We plug back in the machine learning that we just learned, run it forward in time, and we validate the model over this time period. We say, now let's look at the biases that we've potentially corrected. Cool? Everyone comfortable with that? Questions? No. I'm doing a really good job. Okay. Here's our machine learning algorithm. Bummer of a diagram, right? So this is our machine learning model. For those of you who are experts, this is a convolutional UNet. It's got some residual blocks in there. It's not very fancy from a machine learning perspective. I know it looks like a lot of garbage, really, but you can think about this just as a bunch of matrix vector operations that are then activated by nonlinear functions, so it can capture some sort of nonlinearities with the atmosphere itself. We did an ablation study to see what predictor variables were important in order to ensure that we are predicting our target variable, which is our nudging variables. And we said these are the important suite of variables that lead us to the highest skill here. And you'll notice that you can pull out some interpretability here. There's a lot of things that have to do with the surface here. So the surface stresses, some of the surface friction velocities, bottom temperatures of the model, boundary layer height. So that should give you a big clue of what's coming in the future. But then we train this model to predict the nudging increments. So what does the skill look like offline? Yeah, Chris.
So you don't consider any of the static fields?
We have static fields in so much as I do have the terrain in there. I have, what else? No, just the terrain. So that is the only static field that's going in here.
Does it know land versus ocean?
No.
Okay.
No. So we then run this offline on our testing data, and we show that we can get skill. So here is R squared summed across the atmosphere, south to north, going vertically here. And you can see that you have pretty high explained variability here, especially in our storm track regions. That's where we are able to capture the most skills possible. And I'll remind you, there is no observation in this state now. It is just using the model states, predicting the model increment. So we can run this online. So we have a fairly high confidence that we are predicting some of the state-dependent nudging increments here. So this next slide I call Nobody Cares. This is how I spent like 3.5 months of my life on the software linking of these two things. So we're trying to do this. We're trying to accomplish a machine learning algorithm coupled to CSM. So we have CSM, which is an online complex Fortran environment. We have PyTorch, which is a Python environment. And I somehow have to make them talk to each other. And this is a nightmare, truly. So it took me forever to link these libraries, hook them up to the GPUs so that we didn't lose any speed in model performance, and then send this off and be able to run it in real time. Luckily, I was able to work with Jim Edwards, who is a brilliant software engineer at CGD, and Jack, who is one of the developers of FTorch, which is a Fortran binding to the Python library. And we just need to figure out how to hook up the right flags and write new machine definitions for our GPUs. So that was all, at the end of the day, that's all I have to do. I have an email chain with both of these people that are about 160 messages long. So I feel obligated to show this slide. This will now be shipped with CSM 3. So everyone will have access to be able to use FTorch coming up, which is really nice if we want to start impacting, looking at more machine learning-based parameterizations within our model suites. So we'll look at a couple experiments to see if this worked. We have our ML-based correction with CSM. We have our control, in which there is no machine learning. Additionally, we'll just look at using a climatological increment. So this is a non-state dependent, state independent correction in which we're taking the diurnal cycle and the climatology of these increments, reinserting those back into the model, and we'll compare those back to the ERA 5 or if we're looking at precip, the GPCP product. I will guide your eye a little bit. Cowboy hat, smiling, that's our machine learning one. Observations are the skull. I don't know why. So this is a pretty stringent baseline. So Judith and I put out a paper last year looking at developing a stochastic tendency adjustment and a deterministic correction derived from data assimilation increments. Yeah?
So is there a reason why we're using GPCP and
ERA 5. Gridded products that are nice. I know they inherit biases themselves. I've looked at other precipitation products. I've looked at other reanalysis products. These are the ones I'm showing you, but it looks good if you look at Mira or any other ones. If you use strict observations themselves, I haven't done it. It's a real task, but yeah.
So do you have the model resolution? Is it 1 degree or?
Nominally 1 degree, yeah. So Judith and I put out this paper saying that the climatological adjustment is pretty good. So here's one figure that we have in that, looking at the improvement to precipitation just by doing a mean correction. So simple correction here. We get about, for DJF, between 15 to 25% improvements to precipitation. This is globally. If you look over land, all these stats go up more. It never really degrades the model. We couldn't really find any evidence of that. So I will now compare this as a pretty stringent baseline to our machine learning-based system. Cool? Complicated figure, let me walk you through it. So in sense of RMSE, anything left of 0 degrades the model, anything right of 0 improves the model. We have the mean correction, so that climatological correction, and then the machine learning correction in teal. U, V, T, Q, and then surface level variables here on on the bottom. So 2-meter temperature, pretty big improvements here. You can see generally the machine learning method in teal overperforms the mean correction. This is all for climatological biases by season, so precipitation over land, precipitation total, sea level pressure. And generally we are improving by 50% or so in the wind fields, 20% in the lower atmosphere for temperature, little degradation in the mid-troposphere, and pretty solid improvement except the stratosphere in our Q fields. But you might notice something that I noticed. The machine learning method is not that much better than the stringent climatological correction, and I did spend about 3 months trying to get it to work. So I was pretty bummed. I was pretty disappointed, and I took the rest of the day off, basically. So that was until I started to look at more fields that are not climatologically dependent. Like, what if we actually looked at the physics of the atmosphere? What if we looked at more of the variability states? And we honed in really on the Madden-Julian oscillation. So this is the MJO. This is a planetary scale, unstable circulation system. This is a nice figure by the Adamus group here. You can see it's sort of a gill response in the tropics, has extratropical signatures, sends these Rossby waves. It's really, really important for subseasonal and seasonal prediction. Huge component of variability in our climate models. We really got to get this thing right if we hope to have a healthy climate model. So one thing that we have, as a community, have really struggled with is the propagation of the Madden-Julian oscillation across the maritime continent. So this is a figure of the ERA 5 here, showing precipitation in color fill and 850 millibar winds in contour. And what you see is a lagged correlation diagram. So this nice Hofmüller style propagation over the maritime continent here. What we typically see in our control model and even in the mean correction model is we don't get this nice propagation. However, when we add the machine learning, we have a nice propagating state. If you look at the wave spectrum, it looks pretty good. I won't say it's perfect, but there's definitely improvement there. So we wanted to go in and say, is the machine learning doing this for the right reasons? We have a good correction here, but can we dynamically track the sort of chain to see if we can inform on some of our physics here? So what we did is we took a low pass frequency representation of the precipitation in this box that is indicative of the timescales of the MJO. So this is our MJO precipitation. And then everything I'll show you, I'm regressing onto that signal. So this is essentially showing the preconditioning state of before we pass over the maritime continent. And we'll do this in the context of the trio interaction theory. So this is a theory that was put forth in 2016, sort of combining all the mechanisms in which the MJO has been put forward to do propagation. And it really combines 3 big things. So we need lower tropospheric heating east of the MJO center, boundary layer moisture convergence east of that center, and lower tropospheric circulation enhancement. So really a coupling of the Rossby waves and Kelvin waves there. And this leads to a eddy available potential energy generation east of the MJO center, a pre-moistening, and a major destabilization of the atmosphere that allows the MJO to propagate. So we're going to examine all of these boxes in the model to see if we've improved those states. And I'm just checking how I'm doing on time. Great. So lower tropospheric heating. So what I'm showing you here is the diabatic heating rate in the model. So condensation, convection, boundary layer processes. Here is the observation state. What you'll see in color fill is that, and then winds. So what you should see is a nice circulation, Walker circulation, some big response there. And I'll note it's really only in the machine learning correction that we have this nice inflow, this transition from shallow convection to deep convection here that's been added. So we're looking like we're getting some heating east of the MJO center. We have boundary layer moisture convergence. So what this is saying is we need to pre-moisten the atmosphere. You should have some dragging in of this specific humidity east of the center here, typically in this region. We have big problems in our control and our mean state correction, but we do get some representation of it in the machine learning correction. Finally, lower tropospheric heating circulation anomalies. So this is a representation of the Rossby Kelvin wave structure here. So what we should see are these nice Rossby wave signals and the Kelvin wave associated it. Typically we get a good or a strong Rossby wave, but we don't have our associated Kelvin wave unless we enhance or we plug back in the machine learning correction. So that's really the signal that we're enhancing there. So we've kind of put together those old frameworks, so I'll quickly show you the eddy available potential energy. What I really like to look at is this pre-moistening and pre-destabilization of the atmosphere here. So what I have in the background is equivalent potential temperature, and in the contours, specific humidity. So we're seeing a major moistening of the system compared to our control, and also just a really unstable atmosphere. So if you take a vertical gradient of that space and look in the XY plane, what you should see is this nice dipole of red-blue, so super unstable here, and more stability east or west of the center. And you see some evidence of that in the control and the mean correction, but really the smoking gun here is we've really destabilized the atmosphere. The machine learning is adding to that space, and it's allowing us to sort of, as we talked about before, explore more areas of the tractor, encourage that Mann-Julian oscillation propagation. So what do the increments themselves actually look like? Can we learn something? Is there some improvement to the model that we could potentially make? When we examine the increments coming out of the machine learning model, largely they were all focused in that boundary layer area. So above the boundary layer, pretty minimal increments when you do that low pass frequency or low pass filtering. But in the boundary layer, massive increments. Really what we're seeing, I'm taking precipitation, Mann-Julian oscillation precipitation, the red box, and regressing the meridional increments on them. What the machine learning algorithm is doing is encouraging massive convergence east of the convective center, and also kind of shutting down convection west of the center. So to me, when I was talking to Rich Neal, both of us kind of looked at this and said, we're likely missing some heating, or our parameterization process is not getting the heating that is dragging more winds into that area. And then if you look at the actual convective tendencies from the model, so here's the T tendency from condensation in the control simulation and the machine learning enhanced. What we're noticing is that we don't have this big shallow convection region here that then leads to this upscale growth. So it's really this area that we're believing it's the interaction with the sort of top of the boundary layer that we're not getting enough condensation. So to test this a little bit more, what I did was write a really quick Fortran routine. And I said, okay, I want to conservatively map any of the heating from our convection schemes lower in the atmosphere. So I'll take if we're over the maritime continent, and again, this is just a hacky proof of concept, I'll take our deep convection scheme, I will apply a Gaussian redistribution weighting on it that conserves all the heating, and then I will force it lower in the atmosphere. So this just pushes the heating down a little bit. Not the most elegant solution, but what it does do is it leads to more propagation across the maritime continent. So this is indication that likely we're missing some heating in the boundary layer. And if we can encourage that in some other way, potentially we'll have a better MJO. Cool. So really what we're thinking and what we're exploring in this new paper is that the CNN is really affecting these two areas, the lower tropospheric heating and the boundary layer moisture convergence. It then kind of links this whole dynamic system up and leads to better propagation. And that's currently being written up. Our first paper kind of just explores the biases. So I'm happy to chat with anyone who has questions there. Here is just a nice figure that I pulled from a model diagnosis paper that essentially split GCMs into good MJO models and bad MJO models based on their Rossby Kelvin wave response. So with the machine learning correction, this is the same metric calculated here, which I would now classify CSM as a good MJO model compared to the composite here, whereas before, without it, strikingly similar to the bad MJO model. So, yay. Cool. So summary from this part of the talk. Climatological corrections from the or a CNN tendency adjustment can be used to improve climatological biases, right? We both saw an improved correction from both the climatological correction and the machine learning correction. However, a machine learning enabled simulation produces a corrected MJO and the correct dynamic chain for this. So if you want to impact the fast physics, if you want to improve more than just your bias, but you want to get at some of that CRMSE or the standard root mean squared error in a forecast state, you're going to need probably a state-dependent correction. And that's been seen a couple times in a couple studies at this point. So likely we're missing some heating in the boundary layer over the maritime continent. What that is, we're still investigating. So this last point was a pretty technical point that we didn't explore in this talk, but it was really important where in the physics suite I was calling the data assimilation step, and that gave me much more insight into what the actual errors are. And I say data assimilation very loosely, again, nudging when I did this. So that is the first part of the talk. And then we're going to move on really quickly to some of our pure machine learning based efforts to forecast the atmosphere and to forecast the climate. So we just talked about how we can use machine learning to enhance a dynamic model. But what if we replace the model itself with the machine learning? So there's a big effort going on at NCAR right now, led by a bunch of folks, some of that are in the room, in order to explore this space of climate model and weather model emulation. So we have 4 preprints out. We're going to be talking a lot about this first one, but I encourage you to look at all these other ones. It's been a really cool effort. We're moving really quickly in this space. So just to review, in a typical general circulation model, we take some input and we evolve the equations, the governing equations. We resolve some on the grid scale. We do the subgrid physics. We then produce an output, and this is sort of marched out forward in time. In a machine learning-based system, we're essentially going to replace our physical equations with some sort of encoder-decoder that we learn directly from the data. So now, rather than having a dynamic core and a physics suite, we have a big old neural network that's sitting there and correcting it. In order to satisfy some of our physical constraints, what we've done is we've added physical constraints into the neural network itself, so ensuring that it conserves total global moisture, total global energy, total global mass. And we found that this is really improving some of our predictive states. So
are those corrections, is the mechanism the same for both KM and?
no, we do a much more ad hoc version. We're doing total global. We don't conserve on the grid scale level. But it's our first effort into this and kind of innovative in the space. So it's not the same mechanisms, but note we do have correctors in CAM also. So what we've done is created this platform called CREDIT. So this is the NSF-NCAR Community Research Earth Digital Twin, or CREDIT platform. So CREDIT is a research platform for understanding the best practices for training and operating global and regional weather prediction models and conducting science on those models, importantly. So essentially what we've done is we've handled all the pain points within creating a machine learning-based system, specifically around scaling on our HPC, curating the data sets, writing really state-of-the-art machine learning-based method for you, so you can dial these up and then use them directly. We want to see this as something like a CESM for the machine learning space. And to give credit for credit where credit is due, all these folks have had instrumental parts in really pushing this forward at the moment. I want to highlight Dama and Arnold, who are graduate students that have done unbelievable work and have really push this project forward. So this was originally started by me, John, and DJ. Kyle came in and just was an absolute whiz kid also. There's just been some really great progress in this space. And I'm really excited about what we're kind of pushing out into the community now. And I think it's really putting NCAR, giving us access into this big space of machine learning that is kind of growing largely within our field. So what has CREDIT taught us so far? There's a list of things that are all in these simulations here, but the first one are really machine learning based advances. We can compete with tech. Tech is currently asking us for advice. We're sharing. It's really cool. I don't think we need to leave the machine learning to those folks. I think we can handle it in-house, and we are doing it very well. The next 3 or 4 is the fact that if we can do things that we know as atmospheric scientists and oceanic scientists that are good for the model space, we can improve the predictions themselves. Things like using terrain following coordinates and enforcing physical laws are improving our forecast state. And I encourage you to look at Kyle's 2 papers if you want to see those directly. And finally, we're focusing a lot on ML pure climate model development, and we're seeing that we can potentially have a pure climate model that is all machine learning based. Time, doing okay. So what is one of the big motivations for this? So this is taken from a talk from Sebastian Lurch, but yeah, I thought it was really enlightening, and it comes out of this study by Jay Quinting here et al. So if I were to run 40 ensemble members, 2 model runs per day, 365 days, that cost me with a physics-based weather ensemble about $475,000. This is on the German computers here. It's like a nice house in Italy. It's not a nice house here. Can't quite get one here. Any guesses on how much this is going to cost us with our AI weather ensemble? Not a cardboard box. That's the first time it's been lower than the actual, yeah. Any guesses? More? 2,000? 10 bucks. It's like 200 bucks. It's like a bad bike. Like in Boulder, you wouldn't want to ride that bike because you get made fun of. It's got disc brakes in the picture. I don't think you could even get disc brakes. But $215 is kind of a game changer. This is where someone raised their hand. What about training? Yeah, important. About $10,000 to train. So it is significant. Then you get a really good bike. But really, this is 0.04% of the energy cost. So if we can show that these models have fidelity, if we can show that there is some utility here, it is really, really important that we investigate this space. So with the rest of the talk, we'll look at whether we can emulate the community atmosphere model, which is the atmosphere component of CSM. So in order to do that, I conducted a 35-year FHIST run from 1979 to 2014. This is essentially a ocean and sea ice forced run. I then save all these variables at 6 hourly. So I have a 6 hourly time step in my model. I compute some total water and flux forms so that I can do good energy conservation. And then I gather some static and forcing data. I then force the model with the prognostic variables here and here. So surface pressure, surface temperature, UVTQ, and then diagnose this suite of variables here. Run it through the post block, which means it's conserving all these properties, and that's passing through the loss function itself, which is important to note. So it gets better at conserving as it moves forward with its training. I then train this. It takes about 3 days to train on Derecho using 16 GPUs. Here's the model architecture. Again, complicated diagram, but this is state of the art. It is what's known as a cross-transformer UNet. Cooked up for our weather prediction problem. So we forecast this same model with the ERA 5. We then apply our conservation box. We tune and train the model. Importantly, this is about 1,000 lines of code for our model. It's about 1 million for CAM as a comparison. This is 751 million parameters, so it's a big model. I can't tell you how many parameters in CAM, maybe 30, 40, I don't know. Importantly, this isn't that big in machine learning world. It's about 0.4% of GPT-3, so the ChatGPT that you've been using. And it's about 2.8 gigabytes of memory. So we can stick these really easily on a single GPU and march it forward in time. Do I have another thing? Oh, importantly, 500 times speed up over CAM. Huge computational speed up. So we are emulating CAM. I got to name it, so I called it the Camulator. And here's a promo video for it. So what you're looking at is specific humidity at the surface level. You can see nice atmospheric rivers as they impact the coast, a pulsing of the diurnal cycle here. I would argue that if I handed you a camera, and you probably wouldn't be able to tell the difference, at least at this resolution. Here is a developing precipitation climatology. As we run this forward in time for 5 years, you'll see the ITCZ. There'll be a nice pulse of the Asian monsoon, atmospheric river tracks as they move across the Pacific. It's beautiful to watch develop. But again, this is all machine learning based run that you're currently walking forward in time. How are the model biases? They're okay. So Camulator in the teal, CAM in the purple. So essentially we want those lines on top of each other. We can see some errors, especially over southern Mexico and Central America. can't seem to tamp down. And my big bias in 2-meter temperature is over Greenland. This is like my Labrador Sea freezing over. Like I can't seem to stop that bias. So I'm really looking. Right now I think it's linked to the NAO. Our NAO is a little bit weak, and it is in agreement with that being too warm of a state. So we need to sort that out. So if we force it with historical SSTs from 1979 to 2013, we have camulator in the teal and cam in the purple. It gets a lot of the right internal variabilities. It's pushing up towards ENSO. So that's total heat capacity I'm showing there in 24-member ensemble. And if I were to roll it out with climatological forcing, so climatological SSTs, it's stable indefinitely. We don't see any blowups. We can have this. This is a 250-year run, and that can go on forever. Really importantly to me, especially being a model developer in traditional physics models, is this is a 24-member, 35-year ensemble that I completed in 8 hours. With similar computational resources, this would have been 166 days using CAM. So really, it's a game changer. I can go to sleep overnight. It's typically when I sleep. And wake up in the morning and have all of these models run for me. And then I can see where the biases are. I can start to either train more or add data. Like the development cycle is just so much faster that it has really been beneficial rather than, doing it before. I'm really impressed with that about the development cycle. How does ENSO look? Pretty good. Here is the 8 strongest Niños minus the 8 strongest Niñas. The precipitation response has about a 0.95 correlation in the tropics, and then the extratropics, we should expect some internal variability, and we can look at all the changes and say that is internal variability in the states with 8 observed. And importantly, how does it look when you force it out of distribution? So what I did was I applied a 2 Kelvin warming to the ocean state, and then a 4 Kelvin warming to the ocean state. CAM's response is shown in dash. Camulator is shown in solid line. What you can see is for the 2 Kelvin warming, it does okay. And it's never seen these states before. Once it gets up to 4 Kelvin warming, you'll notice that boreal winter is very low. It's never seen a sea iceless state in its training. It's never seen a lot of this ice melting. So it consistently goes, I think we should be colder than this, right? And I keep telling them, we're gonna do CO2 though. And it's like, yeah. But anyway, sorry. So this response here is a little bit encouraging. That's just in the 2-meter temperature field. If you look at the rest of the atmosphere, the responses are a little bit more muted. But if you start to look at some of the variables that you would expect to change, for example, we're looking at low cloud fraction here in CAM versus camulator. What we see is that we're responding way too much in camulator. So we're really not getting those forcings right. You see some good signs, like across the Southern Ocean, looks good. There should be some response in the ENSO region. It's just like way too responsive there. Over Greenland, we should have some response, but I would say if you squint at it and you're the model developer, you're like, oh, that's great. But like if I handed this to the community, it's probably not so good. So our plan now is to run the model out into the future, start training on some future climate states and really trying to see if we can start to generalize a little bit more. What I really want to say about credit is that we're enabling a lot of science here. So these are all the active projects that are sort of going on or in their nascent phases here. These are the partners that we're working with at this point. So I think it's made a big splash. We were just at a big conference. I just presented this at a foundation model conference in New York with NVIDIA and Google and all the people that are in this space, and they're really excited about our product right now. So I think it is an opportunity for NCAR to really center the science, center the physics, and impact the space right now. With that, I'll leave you with a couple questions that are sort of driving my research right now is like, how do we continue to make progress in this space with machine learning? How do we build cost-effective and physically consistent models that push us out to the limits of predictability? How do we understand where those limits are? And can we fuse observational data with models in new ways to constrain some of the uncertainty spaces? And I don't know what this slide is, so I'm nervous. Nope, not going to read that. Thanks and questions.
All right. Great. Open for questions.
Those runs were all done with a certain grid resolution. What's the effect of a refined grid? How does that all change things?
I mean, so we got Seth working on a product on the CONUS 404. We have to retrain, is the facts are. Like, it's not gonna, the nice thing about physics models is you can, dial up the resolution, you still got the same physics there. With these, you're gonna have to retrain and it's gonna take a lot more compute if you wanna go really high resolution. But I've seen a lot of success in that space right now. I think there's some really interesting work going on in RAL right now on downscaling models. And right now we haven't really explored this, the ultra fine, right? Like the super, super high resolution. While there are people doing like, PDE solvers in typical fluids problems and in bigger spaces than we've explored here, and they show success. So while it doesn't generalize to resolution without retraining, we can retrain pretty easily and get a good potential model product out. So I don't ever see these things replacing our physics models. I see them complementing the physics models, improving our compute, basically helping us answer some science questions that we can answer if we trust them enough to represent the fidelity of the system.
Ready?
So yeah, 2 questions on the first part. Looked like you only trained it on nudging winds, not the temperature and moisture. Was there a reason for that? And the second part is, when you modified the heating profile, was that basically just where the cumulus scheme was active? You had that subtle?
Yes, yeah, exactly.
Okay.
So yes to the second point. For the first point, there's a problem with nudging T and Q in CAM. It sends it into an awful climate state, spins it up really quick. I might have fixed that actually with a new, I found a bug in our original nudging code that if you rearrange some stuff, it now looks like it's running out stably. Back when I had done this work, it wasn't the case. So if we just used the winds, it would seem to be behaving really well. So that was the motivation for doing that. It would have been nicer and it would have been easier to explain physically if I could have just nudged T or just nudged Q, especially when I'm looking at convective processes. So, it was a limitation of sort of the tech that we had at the time. But yeah, there are folks using the new nudging simulations that are showing stability for a long time right now. So if I want to go back and repeat all that work, I could do it.
Thanks. So I'm just kind of curious if maybe this is for credit specifically or machine learning models generally. When you're talking about asking science questions, then you're able to run a bunch of simulations from that. What is that process like? Is it just nudging your initial conditions for the simulations and going, or is it changing things within the model? Like,
yeah, you can do a lot, right? Like, so if I feed it to, the same forcing state, it's not going to repeat the same. At a certain point, it will diverge, just like you're saying. You'll add a little noise, or we call it a PERT lim over at CESM in the beginning, and it will develop new modes, and then all of a sudden you have an ensemble that you can look at internal variability. You can start to look at signal noise problems. You can start to look at, some of the big tail events that we hope show up in our climate models. The other big area of science with this, I'd say, is that they are fully differentiable, so you can start to define different loss functions and look at sensitivities to the input space of those loss. Like, it doesn't have to be the loss you trained it with. So I think there will be a whole new field of science that kind of opens up around these things, and people are really starting to explore those questions. I'd encourage you to look at a lot of Greg Hackham's work at UW. He's doing some really cool stuff right now. So cool. I don't know if I answered all your questions.
Yeah, I think so. I guess maybe a quick follow-up on credit in particular. Is there somewhere I can go to stop playing around? Yeah,
absolutely. I don't have it here. That would have been a good thing to include. If you Google NCAR credit, we just released model version 2. You can pull it and run it on our systems. You'll probably run into a couple bumps at this point, but it's newish software. But I just spun someone up on it yesterday, and it worked. So,
Great.
yeah.
Thanks.
Seth.
So one of the key things that you mentioned that was important for credit was adding in the the physics conservation corrections, like at the end of the loop, right?
Yeah.
Are there other, and that's basically saying we know a priori that these quantities are conserved. So let's take our a priori knowledge and apply it to this.
Yeah.
Are there other things other ways that we could take things we already know about physics and sort of add them to the machine learning?
Oh, I mean, it's a big question. There are better ways that we can handle the conservation. That's easy. So taking those off the table and learning the lessons that a lot of people at NCAR already know. What I'm excited about right now is different data modalities. So we don't have to use just the ERA 5. We could use the ERA 5 plus a suite of observations. And they can come in all different kinds of forms. We can feed them in the model. It's just software engineering at this point. Like it is. The beautiful thing about machine learning is it's Legos, right? Like you can take any data and plug it in there and hook it up, and then it will respond to that data. So I'm excited about that. And on the back end, we can also do generation of different things. Like if we wanted to generate NWS reports, we could do that. There's a huge questions of ethics and things around that. But yeah. So I'm excited about some of the other data modalities, essentially.
Kind of along the lines of you left it out there a little bit about the technical aspect of when you applied the increment in the sequence of different physics parameterization calls, there was sensitivity to that, which is interesting because as I understand it, the nudging is only applied to U and V.
Yes.
But you were still seeing, I can understand it was applied to temperature because you might expect it's, removing instability or whatever, but you still saw that even when it's just being applied to U and V.
Yeah, essentially you would just get the atmosphere to dynamically adjust to the new winds, which was, interesting. The keys that we found, so particularly the bug that we found was that we were calling the nudging scheme at the beginning of the physics suite, then running our club scheme, then running our deep convection scheme, and then nudging the model with that difference. So the nudging method was essentially trying to emulate club and the deep convection. So I was getting these wild tendencies. I was like, man, that looks a lot like the winds you would expect from a convective state. And then when I removed that and I went, oh, that's because it's trying to do that, it elucidated some of the actual errors that weren't a result of that. So that's kind of the point I made there. And then I also had to do that right as you had to ensure that the model state was right at the readout of the model. Like when it should be the last thing in your physics call because that's what the nudging is using for reference. None of that made sense, but
No, I think
I
I think that makes sense. Okay. Just replace the parameterizations maybe with
Yeah, exactly. Essentially, the nudging was acting like it was trying to replace the parameterizations, and that's not what we wanted.
especially the microphysics.
Yeah, exactly.
Replace with it.
Yeah. So.
Yeah. Any other questions? I'll attempt.
Thank you. That's a great presentation. I have two questions. First is the focus right now on the climatology or NWP? So if it is NWP, then do we have any plans to have intercomparison with the traditional numerical NWP and AI NWP? I think that would be something a lot of people would be interested in.
Yeah, so we've compared to the IFS. We sort of have two teams. Like I'm doing a lot more of the climate stuff. John, DJ, more interested in the weather prediction problem. We are currently doing like a near real-time product where we take the GFS initial conditions and forecast with that. By our global metrics, we are outperforming the IFS. And I'm very careful how I say that. So yes, but is it a better model than the IFS? No. That being said, ECMWF has their AIFS product, and they are swearing by it, and they think it's amazing. So and I think we have a very similar sort of state with that, though they have 70 full-time employees working on that product, and we have 3. Kind of piecemeal, yeah. So there's a big difference there, yeah.
Yeah, so the output data must come at you so fast. How do you deal with that? Like,
Carefully? No.
It's not a barrier.
Yeah. No, we write Sizzle every other day asking to increase our scratch storage. So we're doing parallel I/O. So all the numbers I said with the 500x speed up, that is with I/O. So it is like if we wanted to not do that I/O, we could be even faster than that. But it is a big challenge, and it's one of the things that graduate student Dama. He's the one that wrote that bit of code. He is a really good computer scientist, and dial it up and it just goes. It's amazing. So.
Thanks so much, Will. I have a question about this idea of linking it to other components of the climate system. And my question is, would you just sort of share some of your thoughts about the advantages of doing this using machine learned models learned on the different components, in particular, avoiding fluxes, avoiding a coupler? We talked about the different timescales. I'm wondering if you could just discuss a little bit about what a climate emulator using end-to-end training or the different component training, what can we gain that is a problem with classical climate models?
I think you should be answering that question. But my thoughts are, I'm excited about coupling this to traditional models, especially the ocean model, because I think we've had limited success on the climate scales emulating the ocean at this point, because it's a fundamentally different task. There are slower modes. We haven't observed the ocean for long enough. It's like when you're training your loss function, you're doing like next time step prediction, but we expect an AMOC like overturning. That's a tall task for a machine learning model. So coupling it to something like POP and actually using their coupler, while it will be a pain, I think there are some advantages there. If you're thinking in total emulation space, huge advantages because you don't have to use the coupler. You can train independent machine learning models and then hook up the fluxes to each other, and that's pretty straightforward. If you train end-to-end, you again run into that problem of different timescales. If the ocean is operating on one loss function, the atmosphere on another, then you have a mismatch there. So in my opinion, and I think what has been borne out by some folks that have been trying this through personal discussions is like training individual component models, then figuring out how to exchange information is still the right way to do it, just because the loss function tasks are different. You could write a one-size-fits-all, but then you'd have to you would still have to run out to the longest mode, which is GPU intensive, and you have to do this gradient accumulation. But you could stop your gradients for the atmosphere at once. So there are ways that you could software engineer your way around it, but be tough.
Okay, I can't actually see the Slido from Ryan, so let's see. Okay, looks like no one's on there, and we are at 3 o'clock, so let's thank Will one more time.